Okay, so what if the secret to life, the universe and everything, wasn't some mystical number, but a glitch in the matrix? A fundamental limit in computer science? It's a pretty wild thought, right? Well, today we're diving into this really cool idea from a recent paper that connects the entire 4 billion year story of evolution with the absolute limits of what a computer can even do. The whole theory is that life is basically a constant hack. It's this incredibly creative workaround against the universe's own rules, and it's been pulling it off by solving problems that honestly should be impossible.
So to get our heads around this, we've got to start with a basic rule of physics. You've probably heard of it, the second law of thermodynamics. Just think about your bedroom, right? If you don't actively put energy into cleaning it, it just naturally goes to chaos. That's the second law right there. And the entire universe on a huge cosmic scale is kind of like that messy bedroom. If you just leave it alone, order just breaks down into disorder.
And that brings us to this huge paradox. I mean, if the whole universe is constantly running down and getting messier, then how do you explain, well, us? How do you explain a planet that for 4 billion years has been doing the exact opposite? Life has just been relentlessly organizing itself, building itself up from these simple little molecules into cells, then into creatures, and then into these ecosystems of just breathtaking complexity. It doesn't seem to fit, does it?
Yeah, this isn't just some small puzzle. It's a direct challenge to how we think the universe works. It's a paradox that sits right at the heart of biology. So let's follow the clues that this paper lays out, because they lead to a fascinating and completely unexpected answer. So here's the central conflict laid out plain and simple. In one corner, you've got this universal law, the second law of thermodynamics, that's always pushing everything towards chaos and simplicity. And in the other corner, you have the undeniable reality of life on our planet, a 4 billion year saga of ever-increasing order and crazy complex structures. It's like these two arrows are pointing in completely opposite directions. So how can they both be true at the same time? All right, so to try and solve this, the paper starts by looking for clues inside biology itself. But here's the interesting part. It doesn't get bogged down in all these slow, gradual changes that we normally think of with evolution. Nope. Instead, it zeroes in on these rare, almost explosive moments when life didn't just evolve, it totally leveled up. These are what scientists call the major transitions in individuality, and you can think of each one as this massive seismic shift in how life itself stores and processes information. I mean, look at this. We go from just loose molecules to contained cells, then from simple cells to really complex ones with all these specialized parts, then from single cells to multicellular organisms like us, and eventually to these huge societies held together by something as abstract as language. Each and every leap completely rewrote the rules of the game. The biologist Carl Woese, a real pioneer in this stuff, put it perfectly. He said that each of these transitions, it wasn't just another step forward, it was more like discovering a whole new dimension. It opened up, and this is his phrase, a truly enormous, new, totally unique evolutionary phase space. It's basically a fancy way of saying a vast, new playground of possibilities for life that literally didn't exist a moment before. And what was the secret ingredient for each of these huge leaps? It turns out it was the division of labor. Think of it like a baseball team. One person can't be a superstar at every single position, right? But when you get a team of specialists together, a great pitcher, a great catcher, a great hitter, they can achieve things that no single player could ever dream of. Well, life figured this out billions of years ago. It learned how to make a group that could solve problems its individual parts just couldn't handle alone. Okay, so that's our first clue. Life levels up by creating these new teams that are amazing at cooperative problem solving. Got it? Good. Now for our second clue, we're going to take a pretty sharp turn into what seems like a totally unrelated world. But trust me, it's also all about problem solving. The theory of computation. What you're looking at here is a Turing machine. It's basically the granddaddy of all computers. The idea is simple. Imagine a little robot with this infinitely long tape of paper. And the robot can only do three things. It can read a symbol on the paper, it can write a new one, and it can move the tape left or right. That's literally it. But here's the amazing part. With just those basic rules, it can theoretically do any calculation that any supercomputer on the planet can do. It defines the very edge of what we call computable. But here's the catch. Even this perfect universal computer has some hard limits. And the most famous one is called the halting problem. Imagine you try to build a program, And the job of this program is to look at any other program you give it and tell you, with 100% certainty, if that program will eventually finish its job or if it's going to get stuck in an infinite loop forever. Well, the legendary Alan Turing proved that you can't. The answer is no. It's impossible to build a program like that. It's this deep, fundamental paradox. No system can fully predict its own behavior from the inside. So a system can't solve its own deepest riddles. But what if you could cheat? What if you could just call for help from something outside the system? Well, in computation theory, they actually have a name for this theoretical helpline. They call it an oracle. So think of it like this. Our little Turing machine is just chugging along, doing its thing, and then, bam, it hits one of these undecidable problems. But instead of just grinding to a halt, it basically sends up a prayer to the computational gods. And the oracle, well, that's the god. It's this sort of magical black box that exists completely outside the system, and it just instantly sends back the right answer. Then the machine can just carry on with its work, having just done something that should have been impossible. Okay, and this is where it gets really, really cool. What if that oracle wasn't actually magic? What if it was just a bigger, more powerful computer? You could create a whole tower of these things. A second-level machine could act as an oracle for the first one, and then a third-level machine could be an oracle for the second, you see? The paper calls this an open-ended meta-simulation. It's like this never-ending ladder of increasing computational power. All right, so now we have our two big clues. On one hand, we have life's major transitions, which create these new super teams for solving problems. And on the other, we have this idea from computer science of a hierarchy of oracles that can solve impossible problems. And this is where the paper connects the two dots. And believe me, this is where it gets really interesting. The hypothesis is basically this. Each one of those huge leaps in evolution, the cell, multicellular organisms, language, each one is life's way of building a new oracle. It's life hitting a fundamental roadblock, a problem it just cannot solve at its current level, and then resolving that paradox by creating a whole new, higher level of organization to get the job done. And apparently, it all works in a cycle. A system exists, right? It's doing its thing. Then it hits a hard limit. So to get past that limit, a major transition happens, and it creates a new, higher level system. Now this new system easily solves the old problems. But in doing so, it opens up a whole new landscape of new, even more complex problems. And so the cycle just begins all over again, constantly driving complexity upward and upward. You can actually see a little toy version of this in something called Conway's Game of Life. All you do is start with a grid of squares and a few super simple rules about whether a square lives or dies based on its neighbors. But when you press play, you don't just get chaos. You get these complex, stable structures that emerge all on their own. You get gliders that travel across the screen, oscillators that pulse. These emergent patterns act like they're storing and processing information. It's a perfect little metaphor for how computation can build complexity from the bottom up, just like life seems to do. The paper has a really cool name for the structure that makes all this possible, a tangled hierarchy. And a great way to think about it is the relationship between a writer and their characters. So the writer creates the characters, obviously. But as the story goes on, the characters' actions and motivations start to influence the writer, changing the direction of the story itself. It's that constant feedback loop between the levels, the parts shaping the whole and the whole shaping the parts, that drives the entire process forward. So, what's the big takeaway from all this? What happens when you look at the entire history of life through this computational lens? Well, it suggests something pretty profound, that maybe, just maybe, we need to think about time itself in a completely new way. I mean, we're all familiar with the other arrows of time, right? You've got the thermodynamic arrow, which points towards increasing chaos and the eventual heat death of the universe. You've got the cosmological arrow, pointing toward the endless expansion of space. But this theory proposes a third, totally distinct arrow, a biological arrow of time. And this one doesn't point towards decay or expansion. It points towards creation, innovation, and this open-ended, ever-increasing complexity. And that's the crucial point. In this model, life isn't just randomly stumbling into more complex forms. It's a directional process. It's a kind of computation that is fundamentally driven to explore, to innovate, and to constantly expand the very definition of what's possible. It's almost as if the universe is trying to understand itself, and life is the engine it's using to do it. And that leaves us with one last really profound question to think about. If this whole 4 billion-year story of life on Earth is just one giant, open-ended computation, constantly building on itself to reach new levels of complexity and awareness, then what problem is it actually trying to solve? What is it all computing towards? And what happens when it finally gets there?